Hello. We will start chapter 3 by introducing concept of a pure substance. So a pure substance is one that has uniform chemical composition throughout. So the first condition is that it should have a uniform chemical composition. For example, examples of pure substance are water, oxygen, nitrogen, etc. So as you can see, a pure substance can be, for example, a single element, such in nitrogen and oxygen, or compounds, such as in water, H2O. To test whether a substance is a pure substance, we can, for example, take water in a tank and take different sample from different location. We will always obtain from these different samples the molecule of H2O. So that means that water in this case has uniform chemical composition throughout. Moreover, a pure substance can coexist in more than one phase. As we know, the different phases are solid, liquid, and vapor. Let's take for example water contained in a tank. Part of this tank is filled with liquid water, and the other part is filled with water vapor. So in this example, we have water that is coexisting in a liquid form and in a vapor form. So if we take samples from different locations, from the liquid water and from the water vapor, we will also obtain the same chemical composition, H2O. So in this case, the water, the mixture liquid vapor, is considered a pure substance. However, let's take the example of oil and water. So if we put oil and water in a tank, the oil will collect on the top of the water, since oil is not soluble in water. So if we take different samples from the two dissimilar regions, we will obtain different chemical composition. So in this case, the mixture oil and water is not a pure substance. In this section, we will talk about phase change processes of pure substances. we will use water in this section to demonstrate the basic principles, since water mainly is a familiar substance. Water in like steam power plants can exist in more than one phase. It can exist in vapor form inside in the boiler device of the steam power plant, and it can exist in liquid form in the condenser of a steam power plant. So we will consider now, in order to understand the phase change process of water, we will consider a piston cylinder assembly where inside the cylinder we have water at a pressure 1 atmosphere and a temperature T1 at 20 degrees Celsius. So this will be state 1. You know that a state is a point where it is described by two properties, mainly here the pressure and temperature. So in state 1, as we can see that the temperature T1 equal to 20 degrees is less than the boiling temperature of water at 1 atmosphere. We all know that at this temperature the water will be in liquid form, and in thermodynamic words we will call it a compressed liquid, compressed or subcooled liquid. A compressed or subcooled liquid means that the water here is not about to vaporize, so it is far from vaporization. So any heat addition, any additional heat here will not make the water to start vaporizing. So we say the water in this case is called a compressed or subcooled liquid. So now we will start to add heat to the water. So we will make a heat input to the water. The temperature will start to rise, and the specific volume V will slightly increase. This will be reflected by a slight expansion of the volume of water, or slight expansion of the piston. During heat addition, we should know that the pressure will remain constant, since if we take a free body diagram of the piston, we have as forces the weight of the piston and the atmospheric force above the piston, and from the water we will have the pressure of the water below the piston times the area. So the pressure here from summational forces in the y direction equal to 0 will be mainly equal to the atmospheric pressure plus the weight of the piston over the area. So since the atmospheric pressure and the weight of the piston are not changing, it means that the pressure of the water will remain constant during the heat addition. So during the if we continue the heat addition, the temperature will rise, the specific volume will rise, since the volume of water will slightly rise. Liquids mainly will expand really slightly when we add heat, unlike vapors. So in the liquid state, we will have a small increase in the specific volume. So as more heat is added, the temperature will rise until it reaches 100 degrees Celsius. So if we consider state 2, we have P2 equal 1 atmosphere, and T2 now is equal to 100 degrees Celsius. So this will be state 2. So for state 2, at this point the water is still a liquid. So the water is still a liquid. But any further heat addition, any further heat addition will cause some of the liquid contained in the piston sealant assembly some of the liquid will start to vaporize. So some liquid will start to vaporize. So a liquid that is about to vaporize is called a saturated liquid. So a saturated liquid is a liquid that is about to vaporize. So a saturated liquid is a liquid that has reached the boiling temperature, as in this case 100 degrees Celsius, but is still completely a liquid. So any additional heat will cause some of the liquid to start vaporization. So state 2 will be a saturated liquid state. So now heating will continue, and we will investigate state 3. So the pressure at 3 is also 1 atmosphere. The temperature at 3 will be equal to the temperature at 2. It will be equal to 100 degrees Celsius. So this is very important, since now the temperature is at the boiling temperature. Any heat addition will not cause the temperature to rise. However, the heat addition will mainly cause the phase change from liquid to vapor. So in state 3, temperature remains constant. in this state there is phase change from liquid to vapor. Like, let's say we are midway of the vaporization process, we can see that some region of the water inside the piston cylinder is converted to vapor, and some region is still a liquid. So as we add more heat, more of the liquid will be converted to vapor form. So heat addition will cause more liquid to vaporize, while T is always constant and is equal to the boiling temperature. So in this case we can see that the vapor and liquid, they coexist. The vapor and the liquid, they coexist in equilibrium at this state. We call this state, we call the mixture in this case state saturated liquid vapor mixture. So once now the phase change is completed, so now we'll at state 4, so this is 3, now 4. The pressure P4 will still be equal to 1 atmosphere, and the temperature at the end of the vaporization is still 100 degrees Celsius, and we will have just vapor inside the piston cylinder. So at state 4, the phase change process is now completed. All the liquid is now converted to vapor, so have only vapor. But here, any heat loss in this state, any heat loss in this case will cause the vapor to condense. So we call this state, the water will be in a saturated vapor state. We should note that when there is formation of vapor, the specific volume will now increase further when compared to when there was liquid. So after completion of the phase change process, we have only vapor, a saturated vapor state, at this state that any heat loss from the vapor will cause some condensation and some liquid vapor to appear. So a vapor, a vapor that is about to condense is called a saturated vapor. So a vapor that is about to condense is called a saturated vapor. So if we continue heating now, since the phase exchange process is completed, the temperature will start to rise again. So here at state 5, the pressure is still the same. Let's say we continue heating until the temperature will reach, like, let's say 300 degrees Celsius. So at state 5, temperature will increase also, and the temperature is above the boiling temperature, 100 degrees Celsius. So T at T5 equal to 300 degrees Celsius, the vapor, so any heat loss here will not cause the vapor to condense. So the vapor is not about to condense. So we call it here, the vapor is called a superheated vapor. So a vapor that is not about to condense is called a superheated vapor. Moreover, we should note two different statements. What do we mean by the saturation temperature and saturation pressure? So now we will explain what do we mean by saturation temperature and saturation pressure. We all know that water boils at 100 degrees. Water boils at 100 degrees. But stopping at 100 degrees in this statement will be slightly incorrect, because water will boil at 100 degrees at a pressure of 1 atmosphere, since the boiling temperature is related to the pressure. So as the pressure is increased, the boiling temperature will also increase. So they are the two parameters are dependent. If the temperature, so the temperature at which water will start to boil at a given pressure is called the saturation temperature. So the temperature at which water or any substance, a pure substance, start to boil is called the saturation temperature. The saturation temperature, of course, for a given fixed pressure. If like we redo our experiment but we increase the pressure, so if we redo the experiment and we increase the pressure, how we increase the pressure? Mainly like we add weights. We add mass on the piston, and now the pressure P will increase. So at T equal to 100 degree, the water will be far from boiling. So at T equal 100 degrees, the water will be considered compressed or subcooled liquid. So as the P increase, the saturation temperature T sat will also increase. Moreover, we can say also for a given temperature, the pressure at which boiling will start is called the saturation pressure. So in other terms, at P equal 1 atmosphere, T sat is equal to approximately 100 degrees Celsius, and at T equal 100 degree, so for a temperature of 100 degree, for the water to start vaporization, the pressure is called the saturation pressure, is 1 atmosphere. The relation between saturation pressure and saturation temperature, so this is P sat, T sat, has an increasing curve. Let's say this is here, we have 50, 100. So for a T saturation of 100, if approximately we have a pressure of an atmospheric pressure, so let's say here the units in kilopascal and the temperature here in degrees Celsius. For example, for a temperature of 150, we have a pressure of saturation pressure of 475.8 kilopascal, which means we have like 4.75 bars. So at a pressure of 4.75 bars, the temperature for which the water will start to vaporize is 150 degrees Celsius, and is called, or the T saturation for a pressure of 4.75 bar is 150 degrees Celsius. So that's why a good example in practical life, like it takes a shorter amount of time to cook using a high pressure pan. So to cook using a high pressure pan, it will take shorter time, since the food will cook quicker at higher temperature. Since increasing the pressure will increase Tsat, the saturation temperature of water, then we will cook at higher temperature, and this will mean shorter amount of time. Moreover, like if we all know that the atmospheric pressure decreases with altitude, with elevation. So we expect that cooking takes longer at high elevations, since the saturation temperature will decrease, so we will cook at lower temperature, and which means that the time required for the food to cook will be longer. Finally, we want to know what do we mean by the latent heat. So latent heat is the energy absorbed or released during phase change. So energy absorbed or released during phase change. So during phase change, so the energy absorbed or released when mainly the temperature is equal to Tsat and is constant. So as we mentioned before, during phase change the temperature will remain constant. So mainly the energy absorbed during the vaporization, during phase change from liquid to vapor. So if we have phase change from liquid to vapor, the energy absorbed is called the latent heat of vaporization. For example, at a pressure of 1 bar at P equal 1 or 1 atmosphere, the latent heat of vaporization for water is equal to 2256.5 kilojoule per kilogram. What does it mean? It is that if we take 1 kilogram of water and is at a saturation temperature of 100 degree, or at a pressure of 1 atmosphere, and the saturation is 100 degree, and the water has reached the saturated liquid condition. So to be converted from saturated liquid to saturated vapor, we need an energy equal to 2256.5 kilojoule for every kilogram of water. So we should know that we start from the saturated liquid state to the saturated vapor state, not from the subcooled to the saturated vapor. From the saturated vapor, so now the liquid has reached the Tsat of 100 degree, and we start supplying energy. If we count this energy absorbed during the phase change to the saturated vapor, it will be equal to 2256.5 kilojoule per kilogram. Finally, I just want to draw the process, the heating process that we did before from state 1, from state 1 to state 5 on a TV diagram. So if we draw in the x-axis we have T, on the y-axis we have T, and on the x-axis we have the specific volume V. So from state 1, let's say this is state 1, we have a temperature of 20 degrees Celsius. So we start adding heat. The specific volume will slightly increase. So as you can see, the slope of the line of this line is high, since the liquid will increase in volume in just a small way. So as heat is supplied to the piston cylinder, we have reached the saturation temperature of 100 degrees Celsius at state 2. So now any further heat addition will cause a phase change at constant temperature, some way in the middle. It was state 3 where we have a mixture of liquid and vapor. Any more heat addition, more of the liquid will vaporize until we reach state 4. At state 4 there is no more liquid, we have saturated vapor, and once the water is completely now vapor and the phase change process has completed, any more heat addition will cause the temperature to rise. We can see the slope of the line here is smaller, since the vapor will expand more compared to a liquid. So we will reach like state 5, for example, and state 5 has a temperature higher than the saturation temperature, and the vapor in this case is called a superheated vapor. So subcooled is far from vaporization at state 1. Heating will increase the temperature. Once we reach the saturation temperature, temperature will cease to rise, and we will have now phase change. Liquid part of the liquid will be converted to vapor by when we add more heat, and at we will have a mixture of liquid and vapor. At the end of the phase change process, all the liquid will be converted to vapor, and once the phase change process is completed, heat addition will make the temperature to start rising again, and we will have a vapor that is far from the saturation temperature, which is called in this case a superheated vapor. See you in the next video.